Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. This video lesson on design is based on the textbook by Turton et al., and we're looking at reactor configurations. So we have two types of ideal reactors, a continuously stirred tank reactor or a C-star, in which we assume that the contents are going to be perfectly mixed, and so the compositions, the temperatures will be uniform throughout the reactor. This is actually a fairly decent assumption for a design of adiabatic or isothermal liquid phase reactions. The other ideal type of reactor is a plug flow reactor. In a PFR, the composition of the fluid changes as it flows through the reactor. Possibly the temperature will also change, but we'll assume that they are not going to change radially. So the plug flow reactor is an unmixed model. And generally, this is fairly good if you have high flow rates and turbulent flow. Typically, as we're making our choices for liquid phase reactions, a single plug flow reactor or a C-star type reactor is going to be, very commonly used. If it's at isothermal conditions, the volume of a plug flow reactor is typically smaller than that of a C-star for the same conversion and temperature. For autocatalytic reactions or autothermal reactions, where the feed is cold but the reaction is exothermic, then a C-star may be smaller. For gas phase reactions, typically a plug flow reactor will be a better choice. If you have a fixed bed catalytic reactor, use a plug flow model unless the reactor is non-adiabatic. Fluidized bed catalytic reactors and non-adiabatic fixed bed catalytic reactors really aren't going to be modeled all that well using basic simulation software. Some more advanced software may be required to get a good model. Now, there's a wide variety of complex reaction configurations that you should look at. And so first we have if the temperature change would be very large for adiabatic operation, then you're going to need to provide heating and cooling. And so we've shown here some examples of how that can be accomplished. So in this one here, we have the material is in small tubes, and then we have a cooling or heating fluid that is going around those tubes. It may be that we're going to inject a diluent so that we have something to kind of buffer the temperature changes. Or maybe we'll put in some intermittent zones of cooling or heating, or inject our reactant at various stages along the way so that we can better control temperatures and concentrations. Oh, sorry about that. Another complex reactor configuration that we need to be aware of is going to be exothermic reactions. For liquid phase exothermic reactions, it's going to be easier to control a C-star because of the high energy content of the liquid. And so a lot of times we'll use a pump around just simply to control temperature, passing it through a heat exchanger, or we can do this in various ways, but this is going to be pretty common. For exothermic reactions, we want to also consider gas phases. So for gas phases, if it's mildly exothermic, an adiabatic packed bed reactor probably is going to be fine. You could expect that maybe you'll get a temperature rise of maybe 50 degrees C, but most of the time that's okay. But if it's more exothermic, then you're going to it's going to have a larger temperature rise. And in that case, we probably want to limit the temperature rise to 50 degrees C. Now that 50 degrees is a general rule of thumb. Obviously, if you have safety concerns, you want to take those into consideration. But in those cases, on the highly exothermic reactions, you're going to want to do some sort of cold quenching or heat exchange between various stages of your reactor. Another case is the highly exothermic reactor that we use a shell and tube style reactor. And so the catalyst is in the tubes and gas can flow on the outside of it. That's actually probably going to be more expensive to build and operate, but does give better temperature control. And then we have the fluidized bed reactor. In this case, the catalyst is going to be a solid bed, but it's going to be well mixed with the fluid, the gas, or it could be a liquid. And in those cases, generally we can have this so that it's flowing in and out. The catalyst can be regenerated, it can be cooled, and this is a way of helping to prevent runaway reactions, control the temperature as well as possible, but it will be expensive to operate. And the final case that we want to consider is the endothermic reaction. Now, the good news is that these are safe. As the reaction proceeds, the temperature will decrease and it will slow the reaction, so you can't have a runaway. But you can need to inject heat so that the reaction will even proceed. And so you're going to use the same configurations as for exothermic. It's just that you're going to be adding hot shots rather than cold shots. So you may need to have some high temperatures in order to get the reaction rate fast enough that you can have a reasonably small reactor. But you're going to have to keep adding heat throughout in order to keep that reaction rate up. Frequently, these are going to be paired with fired heaters in order to get the adequately high temperatures and keep the reaction from quenching out, going so slow that you get essentially no product. So this concludes our set of lessons for reactors, and in our next set of lessons, we'll be looking at separations. Thank you very much for your time.